Welcome to the Explainer. Today, we are diving into a manufacturing mystery where a tiny, tiny measurement error could end up costing millions. We're going to follow a team as they use a classic statistical tool, the t-test, to go from just risky guesswork to real data-driven certainty. Let's get into it.
Okay, so imagine this. Your biggest client, the one you absolutely cannot afford to lose, comes to you with a brand new order. It is a huge one, but there's a catch. Their specs are incredibly precise. So the big question is, can your process actually deliver what they need?
All right, so our story kicks off with a bolt manufacturer. They've just landed this massive order for M12 bolts, but this isn't just any old order. The client needs these bolts for a super high precision assembly, and there is literally no room for error.
And when I say no room for error, I mean it. The precision they're asking for here is just extreme. They need bolts that are exactly 50.0 millimeters long, with a tolerance of just plus or minus 1/10 of a millimeter. To put that in perspective, that's about the thickness of a human hair. Every single bolt has to fall within this incredibly tight window. So how in the world does the manufacturer handle this? I mean, they can't just cross their fingers and hope for the best, right? They need to move way beyond assumptions and use a proper toolkit, one that's built for making data-driven decisions. And that toolkit, my friends, is statistics. The main tool they're going to use is something called hypothesis testing. And the best way to think about it is like a courtroom, but for your data. You basically put your process on trial to see if there's enough evidence in a small sample to make a solid judgment about everything you produce. And in this data courtroom, we always start with the null hypothesis. This is kind of like the presumption of innocence. It assumes everything's fine, that there's no difference, no problem, and your process is hitting the target perfectly. It's the status quo, the thing we're trying to disprove. So how do we argue the case? Well, we use something called the p-value. This little number is the strength of your evidence. A really low p-value, and typically we're talking 0.05 or less, is like finding the smoking gun. It means your result is super unlikely to be just a random fluke, which gives you strong evidence to reject that initial presumption of innocence.
Okay, so let's put this into practice. It's time for test number 1. The quality team kicks off their investigation by asking one really fundamental question about their entire production process. And that question is actually pretty simple. On average, are the bolts we're making really 50.0 millimeters long? Are we centered right on that target, or are we systematically off, maybe making bolts that are just a little too long or a little too short? And to answer this, they use a tool with a really cool backstory. It was invented by a chemist named William Seeley Gossett, who worked at the Guinness Brewery. He needed a way to test beer quality using just small samples. Because of company policy, he had to publish his work anonymously, so he used the name Student, and that's why today we still call his amazing creation the Student's t-test. He even warned that without it, your judgments may become altogether misleading. So for this first test, the team sets up 2 competing claims. You have the null hypothesis, our presumption of innocence, which says the process is right on target. The average bolt length is 50.0 millimeters. And then you have the alternative hypothesis, which is the exact opposite claim, that the average is not 50.0 millimeters. The data is going to decide which one wins. They grab a sample of 30 bolts, they measure them up, and they run the analysis in their software. And it spits out one crucial number, the p-value. And that value is 0.241. So what does that number mean? Well, the critical thing is to see how it stacks up against our evidence threshold, which is 0.05. Our p-value, 0.241, is much, much greater than 0.05. This means our evidence is pretty weak. It's just not strong enough to overturn that initial assumption of innocence. And so, the verdict for our first test is in. The team fails to reject the null hypothesis. Now, in plain English, that means they have statistical proof that their process average is, in fact, centered right on the customer's 50.0 millimeter target. That's great news, right? Well, maybe not so fast. See, the production manager has this nagging suspicion. He's got a feeling that the night shift might be running a little differently than the day shift. An overall average can hide some serious inconsistencies, so it is time for a second, more focused investigation. So now the problem turns into a direct comparison. It's shift 1 versus shift 2. Are they both producing bolts with the same average length, or is one of these shifts systematically different from the other?
For this job, we need a different tool. It's called the two-sample t-test. It's designed specifically to compare the averages of two different groups, like two machines, two suppliers, or in our case, two shifts, to see if any difference between them is actually statistically meaningful. And here is the data they collected. You can see it right on the chart. The average bolt length from shift 2 is clearly a little higher than shift 1. But here's the critical question. Is this a real, significant difference, or is it just random noise in the data? The t-test is going to tell us for sure. So, the team runs the two-sample t-test, and the result? A p-value of 0.000. Wow, that is about as low as a p-value can get. It is way, way below our 0.05 threshold. The evidence here is absolutely overwhelming. The answer is yes, there is a significant difference between the two shifts.
All right, let's bring this whole investigation to a close. After running these two statistical tests, what did we actually learn? What's the final data-driven verdict?
Here's the complete picture. Finding number 1, the first test confirmed the good news. The overall process is on target. But finding number 2 is the real bombshell. There's a hidden problem. Shift 2 is producing bolts that are significantly longer. So the action item is crystal clear. Go investigate what's causing this variation between the shifts.
You know, this whole thing was a really logical journey. First, they nailed down the customer's critical need. Second, they tested their whole process against that target. Third, they drilled down to compare their internal processes. And finally, boom, they uncovered a hidden source of variation that could have totally wrecked the entire order. And that right there is the real takeaway. The team went from a vague assumption, I think the shifts might be different, to complete statistical certainty. Now they know exactly where the problem is, and they can go fix it before it ever impacts a customer. That is the power of data. And this really leaves us with one final thought. An overall average can hide some serious truths. The real question you should be asking is this: what hidden variations might be impacting your own processes?